an entry signal utilizing machine learning, and then the final webinar we will take a look at some of the results from what we've done and then compare it to some other machine learning algorithms. We're going to focus on random forest today, but at the end of this webinar series, we will go over gradient boosted decision trees and neural nets as well. If anyone has any questions throughout the meeting, feel free to put them in the chat box. I'll try and get to them as I'm talking, and if I don't get to all of them, I'll try and go through them at the end of the webinar to address them. All right, here is a little risk disclaimer that you guys should be able to see from FXCM. All right, so today, mainly going to talk about, from a high level, why I use machine learning, the type of problems I think it's useful to solve, and then we're going to dive into some of the first steps, which is mainly going to be centered around gathering your data and what type of data is necessary to get good results. Machine learning, you know, it isn't magic by any means, so it's basically all about, if you're giving it bad data, you're not going to get some sort of magic result out the other side. So we're going to focus on data and how to gather it, what types of data, and then how to kind of clean and pre-process your data, and how to collect data effectively to make the machine learning algorithm more likely to do a good job. All right, so from a high level, the way that I best explain machine learning and think about it is it's just an algorithm or a mathematical equation that more or less allows a computer to search for patterns within data. And this can be done a few different ways. We're going to go over random forests for the most part of this video lecture because they are probably the easiest and most powerful machine learning algorithm to jump into straight out of the box. And there are some really nice packages out there in Python like scikit-learn and XGBoost that allow you to get some pretty great results from a random forest without much work on your part. But basically for the random forest algorithm, what it is learning to do is it is taking each one of your variables that you've collected, and it is testing every single one of those variables to see if it can split on any threshold to split your data in a way that it's going to find patterns, which we'll get to in a second. But more or less, machine learning, you set up an equation, you tell the computer to go run through some data, you give it a way to judge the results of whatever it did during that data, and then it's going to kind of repeat that process and update over and over. For neural nets, we call them epochs, and it's going to kind of update weights in a matrix. For random forest, it's just going to go through your data and try and split the data into halves, more or less, that allow for the most information gain, which again, we'll get to in a second. The ML algorithms that I use in my day-to-day work are mainly decision trees and groups of decision trees, which are called ensemble methods, which are those random forest classifiers. I also use gradient boosted decision trees, probably more than anything else. Some of the packages for that, if people are interested, are XGBoost and LightGBM. Neural networks are very popular right now, especially LSTM, which is long short-term memory models. They are used for in the past have been used for speech recognition quite a bit, but do a really good job with time series. So they are suited fairly well to price data since it comes as a time series. The other thing that I will use quite a bit is evolutionary algorithm, and more or less I will use that to kind of tune the other two. In a machine learning algorithm, there are things called hyperparameters, which we will get to in a second. And these hyperparameters are kind of the tweaks to the math equations that we are using to learn, or telling the computer to use to learn. And an evolutionary algorithm, in specific for me at least, a genetic algorithm, allows me to test a lot of different combinations of these hyperparameters more effectively, so I don't have to run through thousands or hundreds of thousands of different combinations of hyperparameters and potential machine learning algorithm settings, I guess, if you will. The reason I use machine learning for trading is, similar to why all the big tech companies are using it for computer vision and speech recognition. It's just extremely powerful, especially with the added computing power that we have nowadays, whether it's through your desktop at home or Amazon Web Services or anything like that. It will find the pattern that you're telling it to find. That can also be a very large problem, because if you tell the machine to find a certain pattern within a set of data, maybe you're telling it to find trades that gained 1% from open to close one day. It's going to find more or less every pattern that shows or that identifies that label. And with market data, because market data is so noisy and there are so many extraneous factors going on, a lot of times it's going to overfit the data. And it's really, really easy to overfit data in general, especially with market data, but machine learning makes that especially easy. So a lot of my research is focused around, how are we finding the patterns that we want to find, but also leaving out the noise, and just finding that signal. So yeah, that's mainly what my research is focused around. And machine learning makes it really easy to create an incredible looking backtest, basically with very, very little work. But to get that to translate to live trading is obviously quite a bit more work. Okay, so from a high level, the general process and steps for machine learning and for any algorithm in general. The first thing you have to do is kind of create your hypothesis, whether that is you believe, if a stock is down 10% over the last week and it rebounds or V-bottoms on high volume, then you believe there's a good chance it's going to gain 5% over the next few days. Anything like that, or if earnings come out and the earnings are positive and it's an earnings beat, you believe the stock's going to follow through for the rest of the day. You basically need to come up with some sort of hypothesis like that. Then you need to back test that hypothesis. And as a part of Kirshner, we have a back testing engine that we use for basically everything. It's called Quant. Here it is, just www.cloudquant.com. And this allows us to, basically gives any user on the internet access to all US equity tick data back to the beginning of 2011. So this is what I will use to gather my data in the first step of the process and kind of initially test my hypothesis. I'm not going to go into exactly how to code on our system here, but if you're interested, go into cloudquant.com, take a look at the documentation over here, and it will kind of give you a rundown of how to use our system and how to gather data and begin to create and test your hypothesis and use machine learning. The idea that we have with this is to allow people with good ideas to come on and use our services the same the same platform we use to develop models internally to come up with their own models, and then we will allocate funds to those strategies. Anyway, so in here, I would go through and code up my general hypothesis. Probably want to keep it pretty loose. Machine learning needs quite a bit of data to do its job most effectively. So when you're first coming up with your hypothesis, you don't want to constrict the algorithm too much. You know, say if you wanted to, I believe this strategy right here is something like if it is an earnings symbol, which we have in these lists here. So basically saying if earnings were either this morning or last night after the close, and it has gapped up 50% of its ATR, then we want to enter. And obviously that in itself is not going to be a very powerful algorithm. But if we restrict the algorithm more than that and we say, you know, we want it to gap up 50%, we want it to be the first 5 minutes of volume to be greater than 25% of the average volume for a day, and all these other constraints, we're basically doing exactly what we're going to ask the machine to do, except the machine is going to find a more optimal solution to us in most cases. You know, it's going to be, the problem is going to be whether or not that solution is overfitted or not. But basically, so we go in here, we create some sort of entry signal. This one is literally saying if there was earnings, if it has had an opening trade, so basically just saying it's traded once past 9:30 Eastern, then we're going to enter. And there's a simple algo buy here. Again, you can look up what all of this means in the documentation, and I'll include my contact information at the end of this presentation so you can shoot me questions if you're interested in it. But basically, Cloud Quant allows you to very easily capture data in variables in a Python dictionary here. And then at the time of your order, you can collect that data. You can run a back test. And then in our results page over here, you can go to, you can go over here and do download trades as CSV. And if you download those trades as a CSV, it's going to include everything that all the data that you collected in a CSV file that has the matched entry and exit times for that order. So I'm doing this not to, I mean, the sole purpose of this initial step is just to collect data. And I'm going to collect all sorts of different types of data. When I actually do this in practice, I collect something close to 3,000 or 4,000 different variables. And then we'll kind of pull those out in a CSV file and start working with them in a Jupyter notebook, which we will get to in a bit. I've had questions on what type of data I normally collect, and you know, obviously a lot of price movement. Everything needs to be normalized. So if you have a $50 increase in price on a stock like Amazon, that may not be the biggest deal in the world. If that were to happen on a stock that's normally priced at, you know, $2 or $3 and it goes up $50, then obviously that's a much larger change. So, you know, we either normalize things just by percent change. I prefer to normalize things by the ATR, which is the average true range, just because there are certain stocks that in general trade in a narrower range as compared to a larger range. So normalizing by ATR gives a more relative movement to each one of these. And then on top of that, volume is really important. You know, so I'll do similar things with volume as far as the change in volume, and then I will combine those a lot of the times too. So it'll be something like, you know, what was the change or the ATR change in price in the first 5 minutes multiplied by the volume in the first 5 minutes divided by the average volume, you know, or maybe Cloud Quant allows you to see every update of the NBBO, so you can track the total volume that's on the bid versus the total volume that's on the ask, so you can get an idea of what the money flow is, especially if you're trying to fade a position. It can be really helpful to understand how many trades are happening on the bid versus how many trades are happening on the ask. All right, and then back to next steps. After you've kind of created your hypothesis, you've gathered data that you think is going to be applicable to that hypothesis, you're going to label your data. And there are in general, two types of kind of classes of machine learning algorithms. There's classification and then regression. We're going to work with classification today and for the rest of this video lecture. And classification solely means that you are just bucketing your trades into different groups and you're labeling each one of those groups as a class. So a simple example of that could be, we have two classes. One class is positive trades that have, returned greater than 0 for the day, and the other class are negative trades which have lost money for the day. Regression is where you have a continuous label, so it's not discrete, and that would be something like you're asking the machine to predict what the return is going to be by the end of the day. So instead of being just positive or negative, the return could be anything from, it could be negative 10%, it could be negative 5%, it could be a gain of 2%, 2.3%. It can take any number within a range. In general, I've found that regression is more difficult for the machine to estimate accurately, especially with market data, because it is so noisy. So I stick to classification most of the time. I will use regression here and there, but classification seems to do a better job, and it's just an easier problem for the machine to solve. So getting back to this, you need to label your data. This is extremely important and probably fairly difficult to kind of wrap your head around right now in some sense, just because you would think that a label of, if you're doing a simple label of, is the trade a positive trade by the end of the day or negative trade by the end of the day, then that's not too difficult. But if you have a more complex setup, finding whatever threshold you're trying to label can be difficult. If you're looking for trades that only gain greater than 1% by the end of the day, deciding on that can be slightly difficult, and a lot of times you have to try multiple different labels to see what your entry signal can actually predict in some sense. Maybe your entry signal, whether, let's say we're buying 5 minutes after the open on an earnings stock, maybe that's a strong entry signal for the next 2 hours, but by the end of the day, a lot of those trades have rolled over. So if you create your label and you label your data such that you are bucketing your trades into trades that have gained 1% by the end of the day versus trades that haven't, you may not be optimizing that entry signal as well as you could. So you need to try out multiple different labels. The other thing too is, say you label your trade as it's gained 1% by the end of the day, and you put all the trades that have done that into one bucket and all the trades that haven't into a different bucket. If a trade is gained 1% by the end of the day and another trade is gained 0.095% by the end of the day, or 0.95% by the end of the day, those are more or less the same trades, but you've now categorized them in completely separate classes, and the machine is going to find patterns that split those trades apart. So it's going to try and find you the trades that have gained 1% and try and keep you away from the trades that have gained 0.95%. which in some sense you don't really want. You know, you may not want that hard split there. So that's something you just have to kind of be aware of. Another thing with your label is a lot of times you need to normalize it with something different than just the percent return, because again, sometimes a 3%, 4% return in one day for an extremely volatile stock is not that abnormal, but for something that trades in an extremely tight range, a 3 or 4% return by the end of the day may be massively abnormal. So finding exactly how you want to normalize your label is another thing that you're going to have to play around with. And in some sense, this label can turn into another one of the hyperparameters of your model, which we will get to in a little bit. From there, it's really important to split your data into multiple different sets. This is mainly to prevent overfitting and to test how well your algorithm generalizes to data that it has not been trained on. So when you actually go live, your results are fairly similar to what you would expect. Most of the time I will gather data, well, with Cloud Quant, most of the time I'll gather data back to the beginning of 2011, because that's when our data starts. And I will do most of my research and training, if you will, on data from 2011 to 2015. And then I will leave out 2016 and 2017 to kind of be my testing sets. And what I mean by that is I'll take all the data from 2011 and 2015, and that will be the data that I will label as positive or negative. And I will tell the machine to find the patterns within that data. And then I will study those patterns or study what the machine has found, and I will come up with new data points or new variables that appear to be more useful for the machine to split on to make a better prediction. And I will do all my analysis, you know, even outside of just machine learning, on that 2011, 2015 data, whether it's what my targets are, what my stops are, the time frames, my trades, the different labels that I'm trying out, like we were just speaking about. And then I will leave 2016 and 2017 out, and that will kind of be my testing data. So once I've gotten a solution that I believe is decent from the 2011 to 2015 data, I will then move to the 2016 to 2017 data, and I will retest that solution on that data to see how well it generalizes. Most of the time it's not going to be as great as the results from 2011, 2015. So I will then go back and kind of reiterate over my research process and try and improve the results. And by doing that, I am in some sense fitting my data to the 2016 to 2017 data, because every time I go and test on 2016 and 2017, I am gaining more insight into that data, and I am making changes to my model. Even if I'm only researching and making the changes theoretically from 2011 to 2015, I am taking insight from 2016 and 2017 and making changes to the model, and in some sense, like I said, fitting the data and fitting the model to 2016 and 2017, which is why I leave 2018 completely out until the very end of the process for a validation set. So I'll kind of iterate back and forth between the training and testing data. Once again, training being 2011 to 2015, testing being 2016 to 2017, to kind of create my model, doing most of my research in the 2011 to 2015 date ranges. And then when I'm completely done with the model and it seems like it's generalizing well out of sample in the 2016 to 2017 data, I will then finally test it on the 2018 data to make sure that everything is still matching up. And hopefully at that point, I've got a solution that generalizes well to data out of sample and my results look decent. If I don't, and the model does not perform well in 2018, then I more or less need to go back to the drawing board, because if I were going to take those poor results in 2018 and then go and try and redo the model to improve those results, I'm now fitting the data to that 2018 model, and I've lost my out of sample test, which is something that happens a lot with algorithmic development, especially with machine learning, because it's so easy to overfit. Is people will use all of their data, find all the patterns in that data, and they end up just overfitting the historical data. Then they go live, things don't match up, and they lose a lot of money. So this step is extremely important, and it makes the algorithm development process much more difficult, but it's also going to allow you to actually go live with an algorithm and make money. All right, the next step that I will kind of do, which I spoke about quickly, is I will look at my data and I will begin to engineer features useful for the machine learning algorithm. With random forests and gradient boosted decision trees, they don't do feature engineering within themselves. So you need to come up with the features. You need to create the variables that the machine is going to learn from. And with a neural net, which is one of the reasons why neural nets are so popular, is they do feature engineering. So you more or less just need to give a neural net the price movements or the volume changes, and it's going to combine those in ways that it sees most fit. And we'll get to that and how it's kind of doing that in the very last lecture of this webinar. But basically, with a decision tree, which you can see here, so this is an example of one decision tree. A random forest would have anywhere from 100 to 1,000 of these, and they'd all be slightly different variations of this decision tree. But basically what it's going to do is it's going to start with all your data or a sample of your data that it randomly selects. It's going to look through every one of your variables or features that you gave it. So you can see this one is called V2ATR to open. And it's going to look at every potential threshold of those variables, and it's going to split your data according to the labels that you gave it to maximize the entropy or information gain. And that is just a mathematical equation. Basically, if in this original sample, say we had 5 good trades and 5 bad trades, and we split on variable X at the level 2.0, and it split the data into 3 good trades, 2 bad trades, and 2 good trades, 3 bad trades, we haven't really gained much information there at that point. We now have 2 different subsamples that are slightly pure in one sense. There's slightly more bad trades over here and slightly more good trades over here, but we haven't really gained too much information. If we were to instead split on variable Y at, say, level 20, and we got 4 good trades, 1 bad trade, and 1 bad trade, or 1 good trade, 4 bad trades over here, then we would have gained a lot more information out of that split, if that makes sense. So what the decision tree is going to do is it's going to use a function called entropy, and it's going to split on every single variable, every possible threshold to try and create the purest samples in each one of these nodes. And then it's going to split again on, all of the variables, all of the different thresholds possible, until it gets down to a certain maximum depth, which we will specify in the algorithm. This has a maximum depth of 2, 3, 4, which you can tell by, that's our first depth, second depth, third, and fourth. The algorithm, we can specify how many final nodes we allow the algorithm to have, how deep we allow the tree to go, and all of those things will limit the amount of overfitting, but also limit the power of the model. If we allowed the decision tree to have a max depth of 20 and an unlimited number of nodes, it's going to be an extremely powerful model. It's going to find all sorts of patterns, but it is also going to overfit the data pretty badly in most cases. So anyway, this is kind of how a decision tree works. Random forest is just going to be a large group of these decision trees, and each decision tree is just going to get a different sample of the data. So say we have 1 million trades that we're telling the machine to learn from. Each one of these decision trees would maybe look at 100,000 one of those trades, and say we had 30 features we're telling it to learn from. Each one of these decision trees would have 100,000 trades and maybe 7 or 8 features that it's allowed to split on. And the reason that random forest does this is just mathematically. That's what makes it so robust to overfitting, is it forces it to learn from different subsets of the data, and also forces it to learn from different subsets of the features, so that it's not just overfitting the entire data set in some sense. And then once it creates those 500 different decision trees that are all different variations of this based on different samples from the trades and the features, it's going to then save each one of these decision trees as nested if statements, and they're just going to be, it's just going to be a set of rules. And whenever we get a new trade that comes in that we're telling it to predict, it's going to run that trade's data through all of the nested if statements that it created from these decision trees. And based on where that piece of data or that data ends up, it's going to give it a probability of being a bad trade or a good trade, which is just going to be related to the percent of bad trades or good trades in each one of the nodes that it ends up in every one of the decision trees. And then across the entire random forest, it's just going to average each one of those results to get your final probability of being a good trade or a bad trade. And let me know in the chat if anyone has any questions on that and how that works. But basically, what we need to do here is we need to come up with these variables. We need to come up with the data that it can split on to separate the data into good trades and bad trades. And that is outside of my research being focused around not overfitting data, and just kind of machine learning in general. I would say that feature engineering is definitely where I spend most of my time, just trying different sets of variables and different sets of features and seeing which ones are going to allow the machine to split the data the purest. So that's kind of what I'll do, is I'll iterate over this step a few times. We will go over in the next lecture how to tell how much information has been gained from each feature across the entire random forest or gradient boosted decision tree. And from there, you can gain some insight to what type of features are useful. And you can then kind of iterate back to the beginning of the process and create either more features similar to that, or you can try and create better features that are uncorrelated with those features that are already good, because you definitely do not want a bunch of highly correlated features in the same data set. You're going to get better results if you have less correlated features. From there, we will tune the hyperparameters of the model. Again, an example of a hyperparameter would just be the maximum depth. So say we, again, on this one, we limited it to a max depth of 4. If we were to limit it to a max depth of 2, then the model would stop at this level right here with these 4 nodes and would probably generalize better out of sample, but it would not pick up on all the patterns that we want it to as well. So finding that happy medium of maximum depth and then number of leaf nodes, which would be another hyperparameter. And like I said, hyperparameter could be the label that we're telling it to learn from, in some sense. We could tell it to classify a good trade as anything that gained more than 0.5% during the day, anything that gained more than half an ATR during the day, anything that gained more than 2% during the day. There's an unlimited number of possibilities there. And depending on whatever label you give it, the machine's going to be able to find better splits or worse splits. So that can be another hyperparameter. Anything from when we're training our model, how many years of data do we give it to learn from is a hyperparameter that I have in all my models. If I have a lot of data on a certain setup, a lot of times I'll only give it the previous year's worth of data to learn from, so that it's only learning from market conditions that are fairly similar to what it's seeing in the future. If it's a setup that I don't have a lot of data on and seems to generalize well across multiple market regimes, I will sometimes tell the machine to learn from the previous 3 years worth of data. But that is just another example of a hyperparameter. And the reason that I use a genetic algorithm for hyperparameter tuning is just because you change one hyperparameter in the model and it affects the others in some sense. You can't just linearly improve each one of the hyperparameters and assume that if you incorporate all of those together, it's going to be the optimal solution. You need to try multiple different combinations of all those different hyperparameters, and that can be extremely computationally expensive, which is why something like a genetic algorithm, which will learn from the previous generation and learn what combinations of hyperparameters were useful before, and then kind of breed based on those useful hyperparameters and combine those useful hyperparameters into the next generation's hyperparameters, which we won't really get into too much, but happy to share some information if people want to ping me afterwards. And then, so once we have created our features, we've tuned our machine learning model with the hyperparameters, we're then going to train our model on a walk forward basis, which is basically just saying, if we're back testing from 2015 to present, I would train January 1st through January 31st of 2015 on data from January 1st, 2014 to December 31st, 2014. And then for February 1st, 2015 to February 31st or 28th, 2015, I would train data from February 31st or February 1st, 2014 to January 31st, 2015. So basically just for each month, I'm going to retrain the model from the previous year's worth of data and take that as my final predictions to bring into my backtest. And the reason we do that obviously is to train the data on the most up-to-date and recent data. Sometimes I'll retrain every week. I've heard of people retraining every day. In practice, sometimes it can be difficult to retrain every day because you're assuming that you have the data available to you the next morning, and data vendors don't always work like that. So for me, I just retrain every weekend because it is practical and it allows me to train the model on some of the most recent market conditions. So it can learn from the previous week's trades to then take the next week's trades. So from there, once you get your predictions, I will research how to kind of put on my trade or the trade expression. So once I get my entry signal, how I'm going to actually enter my trade. If I'm going to be taking liquidity, providing liquidity, things of that nature. If I'm going to be entering all at once or kind of laddering into a position. And then this last step, which has a lot more involved in it than just finishing your algorithm to manage your position, risk control, etc. I would say that creating alpha, finding the entry signal is probably actually one of the easier parts of the algorithm. Managing your position and exiting your position effectively is definitely what I've found to be the most challenging. But we're going to focus on kind of creating alpha for this webinar. All right. Yeah, so more or less that is, that's kind of what I had planned for today. We can go back here quickly to just the different types of machine learning algorithms. I've kind of explained the random forest a little bit. Gradient boosted decision trees are another very popular machine learning algorithm that I use a bunch, which is where it's more or less going to create these decision trees in one after the other, and it's going to try and minimize the loss function of the previous decision tree at the next iteration of the next decision tree. So it's just a slightly more powerful model. We will, in the final lecture, kind of go over the improvements you'll see from this, but it's also going to overfit the data more because it's going to build a decision tree and then learn where that decision tree messed up in some sense and try and minimize that in the next one. And once again, for these two, feature engineering is hands down probably the most important step, followed closely by hyperparameter tuning. In Cloud Quant, we have access to all the tick, minute, and daily bar data for every U.S. equity since the beginning of 2011. This is updated for every change in the national best bid, best offer. We also have a lot of TA-lib technical indicators, whether that's relative strength index, money flow index, all the moving averages. We're integrating a lot of alternative data sets, things like Alexandria, which is a NLP-driven machine learning data set that basically looks at news stories and will assign a sentiment score to them. So you can kind of create alpha signals based off of the news, similar with StockTwits, SMA. We have another one called RavenPack. We are integrating Morningstar soon, which is going to allow for access to fundamental data, and then all sorts of other things. We've got opening and closing imbalance data. We've got earnings lists. You can tell which type of stock or what stocks had earnings this morning or last night. ETF lists if you're trying to do some sort of basket trades, things like that. And from there, like I was saying earlier, I will kind of create these combinations of volume and price related data and create geometric variables, which is just going to be a way for me to, in some sense, kind of paint the picture of what this stock is doing on the day to the machine. And then with a neural net, again, you wouldn't really need to do this. A neural net is more about tuning the hyperparameters and tuning the model so that it creates features effectively. And during the next webcast, which I believe is 2 weeks from today, I'll actually dive into the code and how to kind of begin to, split your data, label your data, create your features, and then we'll actually train a model and see the improvements that we get from the different machine learning algorithms. And then in the final step, we'll kind of bundle that all together and create an actual algorithm, and we'll show you guys the the backtest results over here on Cloud Quant, and hopefully we will have some sort of decent looking backtest from the random forest, from the gradient boosting decision trees, and from the neural net that we can compare. So if you guys have any questions, that's about all I have for today. Name again is Trevor Trinkino. Feel free to email me at this email address here. Check out Cloud Quant if you're interested in it and would like to start just playing around trying to gather the data. If you want to read some more on this topic, there is a great machine learning textbook called Hands-on Machine Learning with Scikit-learn and TensorFlow at this link right here. Very recently, there has been probably the first of its kind, a machine learning for financial applications, I believe it's called, textbook that came out that's actually pretty great. It is written by a guy who has managed multi-billion-dollar funds using machine learning, and can get kind of in the weeds of some of the math here and there, but is extremely applicable to this, and probably the first of its kind. Other than that, online classes are where I've learned a lot of this stuff as far as the machine learning goes. For this, these are either free or extremely cheap, and most of the time you can learn quite a bit from that. So yeah, if you guys have any questions, feel free to send them to me, or ping me in the chat right now. It doesn't look like I see any questions from anyone. Oh, 1 second, there we go. We got some questions. All right. All right, so we've got one saying, is machine learning the same as artificial intelligence? Yeah, machine learning is just I would say kind of a subset of artificial intelligence. I think artificial intelligence is probably more where you create an algorithm that it's probably like the next evolution of machine learning in some sense, where you create an algorithm that can learn from itself, but then on top of that, you're telling it how to then change the algorithm and kind of iterate the algorithm and improve that algorithm in some sense too. So not only is it learning a certain task, but it's also learning how to optimize its algorithm. But yeah, machine learning more or less is a subset of artificial intelligence. This video is being recorded. I believe FXCM is going to post it on their YouTube channel, as well as we will post it on Cloud Quant here. I believe it takes a few hours to kind of get it up, but we will post it probably by the end of the day is my guess. Can you show a simple model with SMA? I'll include SMA in the model that we kind of build throughout this webinar. So I will, I'll include some alternative data sets in my feature set, and we can see how we can rank their feature importance and see, if it's worthwhile to use or not. Some of the signs of overfitting. Yeah, so it's a good question. One of the biggest signs of overfitting, so while we are, when we go back and we split our data into training, testing, and validation sets. So say this is not really a good example. Let's say this is our back test here, and our training data was from 2014, which is the beginning here, to say 2017. And we have a certain Sharpe ratio of 1.6 up to that point. And then, from 2017 on, obviously if the algorithm starts losing money out of nowhere and you're really looking for like a break in the trend. You're looking for, you want your training and your testing sets to have similar Sharpe ratios, similar edge per share, similar return. Obviously your testing is going to be slightly worse, but if you're using a machine learning model that is too powerful, so back over here where we had our decision tree, say we're using a decision tree that has a max depth of 10. So this can go down for another, 6 layers below this. That's a pretty powerful model, and in my experience, probably a max depth of 10 is a little bit too deep for a lot of market data. What you're going to have is your results are going to look great in the training data. So when you're training it from data on 2014 to 2015 or whatever, your stats are going to look absolutely great. And then as soon as you try and make a prediction out of sample, your stats are going to drop off dramatically. So you more or less, you want to, and this is slightly difficult to explain without being able to draw something here, but you want to, as you're training your data, you want to see similar statistics on the time period that you're training in sample to the time period that you're training out of sample. So, if you're going to tell the machine to find patterns from 2013 to 2015, and as it's finding those patterns, you can actually, there's something, especially with random forest, there's something called an out of bag predictions, which basically it's going to make a prediction on, when it takes a subsample of the trades in here, the trades that it left out, it will then make a prediction on those trades, and you'll get some sort of an estimate for what the model should do out of sample, although that doesn't work very well with market data because obviously returns are correlated. So if you're training on the same day or same time frame, and you learn from half the symbol universe, then you're going to gain a lot more information on the second half of the symbol universe. But anyway, so it's basically you want to see similar statistics in sample versus out of sample, I guess would be simply how to look for it. All right, going back up here. Cloud Quant uses all Python. I use all Python. Python has kind of become the de facto or the kind of par for the course machine learning language, and there are incredible libraries, open source libraries that you can use. It is not as fast as a language like C++, obviously, but TensorFlow, which is the language or the package that I use for neural nets, will actually, it runs everything in C++ under the hood. So that makes things really nice. Python is just a wrapper on C++. And then, so most of the time frames that I'm training in, my trades will be anywhere from 30 seconds to a few hours. We will do some stuff that is multi-day, but more or less right now, our firm kind of specializes in intraday. I wouldn't say we're high frequency by any means. We do have some technological and speed advantages over like a normal retail broker, but we're not competing for nanoseconds. We're not trying to beat everyone to the punch there. And I will share my documents as we, I'll share this presentation on cloudquant.com with the YouTube video. In the next lecture, when we kind of get into the Jupyter notebook here, I will share that with everyone as well. I'll also include a sample data set so you guys can go in there and start playing around with. Let's see. And then I would, if you're looking for kind of more fundamentals on this, I would definitely take a look at these two books, especially this first one here, the hands-on machine learning with scikit-learn and TensorFlow. The first 60 pages or so are really nice, kind of simple, just walk through of A to Z, what a machine learning project is and what the kind of different steps are. So if this, I'm sorry if this was kind of complicated. I'll try and keep things as simple as possible for the next few lectures as well. But if you're looking for more fundamental stuff, take a look at this first textbook. And then also just online classes are great and cheap. Okay, back here. So we had a question on how do you actually get the results from this decision tree? So let's say that we're not doing a random forest and we're just doing one decision tree here. And this would apply to a random forest as well. A random forest is just a group of these, but let's just assume we're doing one decision tree here. And the question is, how would we actually make a prediction with this rule set? So say we have a trade up here that has all of the data listed with it. So we have a trade that we haven't told the machine to learn from, but we have captured all the relevant variables at the time of potential entry. And we want to make a prediction, more or less, if that's going to be a good trade or a bad trade. We're going to feed that trade down here. We're going to take a look at this first variable, which is V to ATR to open, and we're going to check to see, is it less than negative 0.0773? If it is, then we're going to feed that trade down here. And we're going to look at our next variable, which is going to be minutes from open. If the minutes from open is less than or is greater than or equal to 0.77775, then we're going to feed it down here. Now we're going to look at this next variable. If our V to ATR to minutes is not less than 5.1894, then that's going to be false. We're going to go here. And then again, V to ATR to minutes, if it is less than 19.0178, then we're going to go here. This class has more good trades than bad trades. You can actually see here there's 57 trades that we labeled as good versus 33 trades we labeled as bad. So that's going to be almost a 60% chance, or around a 60% chance, that this is going to be a good trade. So this trade, by going through this decision tree, has now been given the probability of 60% of being a good trade. So that's how we would kind of save our rule set through a decision tree here, and then make a prediction in the future on whether or not a trade was good or not, if that makes sense. What tools do you need? I would say, honestly, you really don't need that much. I would say go to one of these online classes, learn how to do some simple Python first, pick up one of this book, probably this first book on hands-on machine learning with scikit-learn and TensorFlow. I would recommend downloading if you just go into Google here and you type in download Anaconda, this is going to kind of download Python onto your computer, as well as download a Jupyter notebook, which is what we're going to be spending most of our time in during the next class, which allows you to pretty easily kind of iterate and research over some data. So that's basically all you really need. From there, go into Cloud Quant here and go over to our documentation and take a look at how we've built our system and all the different callbacks and everything we have. And feel free to ping me with any questions you may have along the way. Again, email is right there. Do you run tests? We do not. Currently, it's all U.S. equities. We are looking to potentially incorporate other asset classes in the future, but right now we just have U.S. equities. How much time between idea and final result? It will take me anywhere between 3 months to a couple weeks to build an algorithm. I would say that a large part of that is focused around this last step, which I've just kind of grouped into finish algorithm and manage position, but that is obviously a massive step. Once you kind of have these processes in place and you've created tools for yourself, you know, it could be, I mean, it could take me under 24 hours to get an entry signal that I think is viable, and then I'll kind of begin working on the rest of the algorithm from there. So the machine learning part the one nice thing about the machine learning is once you have it figured out and you've created the tools that you need, it's a pretty repeatable process. You know, it takes a while to kind of create these tools in the beginning and understand every step, but once you have done that, you know, obviously the machine can do research much faster than a human can. So, you know, it won't take you that long to kind of get an algorithm up and running. Cloud Quant is free. You can go on there and, you know, program away to your heart's content with all of our data. And, you know, if you create a good algorithm, there is a little button here. You know, if you backtest an algorithm and it has a decent looking Sharpe ratio, you can go in here where it says results, and you can just do fund my strategy right here. So you get a backtest that looks something like this and it looks good. Click fund my strategy. You're going to send it to our kind of quants and the guys who are evaluating the strategies. They're going to take a look. They'll be in contact with you, and you know, maybe you'll get allocated some money. I think so far in the last year we've allocated $72 million. So if you're interested and you know you want to give it a go, I definitely recommend it. Once again, feel free to reach out to me with any questions along the way. I'm happy to kind of help. Yeah, so we have a question that's asking what's the minimum number of trades you want to see during a time period so you don't curve fit the data. Normally, I like to see over 100,000 trades in a period for training. If you are using a model that only has a maximum depth of, you know, or using a decision tree and it only has a maximum depth of 2, so right here, you probably only need 20,000 trades. Like that model is probably simple enough to where that's not going to overfit, but most of my models will probably have a max depth of anywhere from 5 to 8, and they are, if I'm using a decision tree, it's probably a gradient boosted decision tree, so it's more prone to overfitting. So I'd rather have 80 to 150,000 plus trades for a training time frame. Do you train them locally on your computer? So I'll train some of my models locally on my computer. I do use AWS for almost everything now. The final training of the models doesn't necessarily take too long, but tuning and trying the hundreds of different combinations of hyperparameters definitely takes a while. So for that, I will use AWS and just spin up a big machine on there. The other thing that I probably run into more is the RAM restrictions. On my local computer, I think I have 64 gigs of RAM, which is quite a bit compared to what most people have on their desktops or laptops. But on AWS, sometimes I need to spin up a machine that has, you know, 250 gigs of RAM that can handle the data set that I'm working with at the time. Would you be able to have a PDF for your slides? Yeah, so these slides we'll throw them into a PDF and put them on Cloud Quant. If you cloudquant.com, if in the press up here, we'll throw them in there with the recording of this video as well. Can I begin to use these tools? So if you want to use these tools, I would say learn Python. it doesn't take, I would say it takes a couple weeks to learn Python. It's a really simple programming language. Go into Cloud Quant here, start collecting data, download Anaconda, bring that data into a Jupyter notebook, start playing around with it. And then, either by using probably the recording from the next webinar is where we'll actually go into the code for creating a random forest, or that book that I included on the last page here. Those would be good spots to start. How do you connect TensorFlow with your trading platform? We have in Cloud Quant right now, we support scikit-learn, and I believe we support TensorFlow as well. If we don't support TensorFlow, we're looking to support it very shortly. And more or less what you can do is you can save, in scikit-learn, we save the classifier or the regressor as a pickle file, and then we just kind of import that pickle file into Cloud Quant, and we can use that to then make decisions and predictions in our models. For TensorFlow, we would just import the weights matrix and then make decisions based on that. So, we are looking to kind of incorporate new data science packages as often as we can. And, from there, you can just kind of import those files either through pickle files is what we normally use, or any other type of files. And then you can just read those files in to your strategy and make your predictions based on that. Namely, this can be, I think this could definitely be brought to cryptocurrency trading. I think there is one thing that one issue with cryptocurrency trading is just getting the data. I think it's probably more difficult to get data. I know there have been talks at Kirshner here and with Cloud Quant of potentially getting cryptocurrency data. I don't know what the time frame on that is. I believe we were potentially trying to do that by the end of this year, but not sure if that's going to happen. But yeah, I do. This can be applied to any sort of signaling problem there is out there. And yeah, in the next video, I will kind of go into the actual code that I use to create this, so you guys can kind of get a better understanding of what I was talking about this whole video. I think that is it. If you guys have any questions, again, feel free to shoot me an email right here. If you want to check out Cloud Quant or Kirshner Trading, here are the websites. Here are these books to take a look at. And I will look forward to chatting with you guys in 2 weeks. All right, thank you.